Nuclear chemistry continued. Nuclear equations with alpha, beta, and gamma particles. So nuclear equations show how an atom or atoms decay or convert to other atoms or other particles. And the easiest way to think about this is that you're going to be balancing two things on either side of the nuclear equation. The total mass number, A, must be the same on both sides. In other words, you count up all the mass numbers on the left, they should equal all the mass numbers on the right. And the same thing goes for all the atomic numbers, Z. All the atomic numbers on the left should be equal to all the atomic numbers on the right. In other words, for the mass number, your total sum of all your large particles, protons and neutrons, must be the same on the left as it is on the right. And your count of atomic number, which is protons, must be the same on the left and on the right. Though, remember, beta particles behave like a -1 atomic number, so it's not exactly the same thing. But as long as you keep the top and bottom numbers of an isotope symbol constant on the left and the right, the sum of those numbers on the left and the right, your equations will look good. So we're not going to worry about balancing charges in this particular unit. Since electrons are removed in a lot of cases, you're breaking apart the nucleus, and that's where we're focusing. We're not going to worry about balancing the charges, especially of the electrons that might be missing. Now, they differ from chemical equations because now the type of isotope, the type of nuclide is very important. In other words, elements may change into other elements. Certainly elements, the isotopes of certain elements may change into other elements. Sometimes they're only changing slightly, sometimes they're changing quite a bit. The new atomic number that you get on the right side of the equation will always tell you what the new element is. So when you change an atomic number, you just look on the periodic table to decide what the new element is. Some of the mass in any reaction will be converted to pure energy. What do I mean by that? Well, when you have gamma particles, they're all energy, and the energy comes from somewhere. Some of the mass in the left side of the reaction has been converted to energy using the equation E equals mc squared. In other words, the tiny bit of mass that might be lost, you would multiply that by the speed of light, c, squared, to get the amount of energy that's actually produced in the reaction. Now, we won't be doing that in this unit, but you'll notice c is a very large number. So when you multiply mass by a large number squared, you get an enormous amount of energy for a small amount of mass. And that's the important take-home message here. But any particle that is released, even mass particles, like alpha particles, beta particles, protons, neutrons, they're all released with a certain amount of energy. They're flying off with a certain velocity, and that has a certain amount of energy associated with it. So that energy comes from some mass that was lost, a small amount of mass that was lost, and converted into pure energy. So let's look at some examples of nuclear equations. First, we're going to start with an alpha decay. And in any of these equations, you have a radioactive nucleus that you start with, and it becomes the new nucleus, and some particle, an alpha particle, a beta particle, a gamma particle. That's where you're going to you're focusing on the alpha, beta, and gammas. Occasionally, you'll see proton and neutron. And then when we look at fission and fusion reactions in a later module of this unit, you'll see that there might be multiple neutrons produced in the process, or even multiple protons produced. But let's focus on alpha decay first. Remember, anytime you see an alpha particle, think helium-4 nucleus. In other words, 4 protons and a total of 4 protons and neutrons. That means 2 protons plus 2 neutrons. So the mass number is 4, the atomic number is 2. And as long as you remember that, these equations will be very straightforward. You're going to anytime you release an alpha particle from a starting radioactive nucleus, you're going to subtract 4 from the top number, the mass number, and you're going to subtract 2 from the bottom number, the atomic number. So let's look at a couple examples. Here's an example on the left with polonium-210. You'll notice 210 is the mass number, otherwise known as the isotope number. polonium has an atomic number of 84, and that is true for all polonium atoms. And this will undergo an alpha decay. And you'll notice in the two examples I show alpha in two different ways. They mean exactly the same thing. You can write it as alpha 4 and 2 or helium 4 and 2 because an alpha particle is a helium 4 nucleus. So you see that the polonium 210, you remove 4 from the 210 to get 206, and you remove 2 from the 84, because remember, you're removing 2 protons, so 84 becomes 82, and you're removing 2 protons and 2 neutrons, so the 210 is dropped down to 206. You've lost 4. Likewise, if we look at thorium-227, we can see that you subtract 4 from the top, you get 223, subtract 2 from the bottom, you get 88, and then you just look up what 88 is in the second example. In the first one, you would have looked up 82 and saw that it was lead. In the second example, you look up 88 and you see that it's radium, and you just write that symbol in there to complete your equation. So let's look at an example where we work through it. Radium-226 undergoes an alpha emission. What is the product? And this is a typical type of problem you might get on a test. Well, first you're going to write what you do know, which is that you start with radium-226. You look up on a periodic table that radium is 88, the atomic number is 88. So you have your starting isotope, your starting nuclide. And you know you're producing an alpha particle, so write the alpha particle product with the 4 and the 2. And it doesn't matter if you write He for helium or alpha, the Greek letter alpha, they mean the same thing. The important part is that you have a 4 and a 2 anytime you hear alpha particle. And now you're just making sure that the sum of all the mass numbers on the left, which is 226, equals the sum of all the mass numbers on the right. So you know that something plus 4 must equal 226. Likewise, the sum of all the atomic numbers on the left, which is 88, must equal the sum of all the atomic numbers on the right. Something plus 2 must equal 88. So obviously we're starting with 226 protons plus neutrons. 88 of those are our protons. If you want to keep track of neutrons, you see that's the difference, 138, but it's not necessary in this problem. And we know that in our final product, our unknown, we're going to lose 4 from the top number, so we'll get 222. And we'll lose 2 from our bottom number. We're losing 2 protons. We'll have 86. And then it's a matter of looking up what is element 86. If you want to follow through and find the neutrons, you can. It's 136 because remember, you lost 2 protons and 2 neutrons. This makes sense. So we now know the mass number, the number of protons and neutrons, will decrease by 4, and the atomic number, the number of protons alone, will decrease by 2. And this will result in 2 numbers, 222 mass number and 86 atomic number. We then look on our periodic table to what is atomic number 86, and that is radon. In fact, the name radon was created because it was named after the 2 words radium emission, and then they combined the words to shorten to just be radon. And so we end up with a product of radon-226, and you would write it this way with radon-222, and you would write it this way with 222 on the top and 86 on the bottom. And that's our answer. So now let's look at another kind of decay, the beta decay. Again, we're going to start with a radioactive nucleus, we're going to produce a new nucleus, and the beta particle. So the beta particle, we're going to label as either an electron or a beta particle. It doesn't matter which, as long as you have the numbers right for the mass number and the pseudo-atomic number. So the mass number will be 0 because it doesn't have much mass. It's not a proton or a neutron. But because release of this results in a neutron becoming a proton, we're going to call its atomic number -1. And that is obviously because the neutron is converted to a proton. And here's the reaction of when the neutron is converted to a proton. So you start with a neutron in the nucleus, and this can happen as a free neutron, but in a atom that's going to have a beta decay, one of the neutrons will undergo this decay. It will convert to a proton, and the number for proton is 1 mass number. That didn't change, but its atomic number is now 1 because it's 1 proton. So in order to make the numbers balance, we give a -1 to the beta particle, to the electron that's formed, so that the 1 plus the -1 on the right side of this equation will equal the 0 with the neutron on the left side of the equation. So it's really a number there to keep the balance right. And if you remember the 0 and -1 for a beta particle, it'll make everything easy. Now you'll notice there's a third particle formed, but we're not going to worry about this particle. This is an antimatter particle called the antineutrino, and it's only for very advanced forms of studying nuclear chemistry, so we're not going to cover it. And you don't have to worry about it. You don't even have to write it. Just remember that the neutron, if it's going to undergo a beta decay, will release the beta particle, that electron, and result in a new proton form. And inside an atom, that just means you lose a proton, lose a neutron, you gain a proton, the mass doesn't change, but the atomic number will go up by 1. And this is a little odd for people to remember because you're losing a particle and yet you're making the atomic number go up by 1. So it's very important you remember that it goes up by 1, but more importantly, just remember the beta particle has associated with it the numbers 0 and -1, and if you do that, all the math will be very straightforward. And you'll notice in these two examples, we have carbon 14 becomes nitrogen 14, the mass number doesn't change, but the element changes. It goes from 6 to 7 in the atomic number, and that means you're converting carbon to nitrogen. And how do you know that? Well, if you just fill in the blank with a beta particle that you know has the numbers 0 and -1, and then just make sure that all the atomic numbers on the left, which is 6, equal all the atomic numbers on the right, 7 plus -1. 7 plus -1 is also 6. The mass numbers don't change. You're going from 14 to 14. And the same thing happens in the second reaction where we have gold, Au, 2O2, decays to mercury, 2O2. Mercury has an atomic number of 80. It's the next one on the periodic table. So you would just find what number 80 is. You would see it's mercury in that case. And you have your beta particle. And you'll notice I've written the beta particle in 2 different ways. So here's an example of a typical beta emission problem. Cobalt-60 undergoes a beta emission. What is the product? Well, start writing what you know. You know that you're starting with cobalt-60. You look up on a periodic table that cobalt has an atomic number of 27. So you have your two starting numbers, 60 and 27. You know a beta particle has the two numbers 0 and -1. And now your job is to just make sure the sum of the top numbers equals the sum of the top numbers on the right. And the sum of the bottom numbers on the left equals the sum of the bottom numbers on the right. And it's as simple as that. So we're starting with 60 and 27 for our mass number and our atomic number with 33 neutrons. And we end up with the proton plus neutron number not changing because we're just converting a neutron to a proton. We're not changing the total number. It's still 60. But the protons go up by 1, and that becomes 28. And if you do the subtraction, you see that you now have only 32 neutrons. Remember, 1 neutron has been converted to a proton. We started with 27 protons and 33 neutrons, and we end up with 1 extra proton and 1 missing neutron. 28 protons, 32 neutrons. And so the mass number is unchanged. The atomic number increases by 1. But I want to point out, instead of doing this addition and subtraction, you never know which thing will be blank in your equation. It could be, you could be given the starting material and asked for the final nucleus, or you could be given the final nucleus and asked for the starting material. As long as you input for the beta particle 0 and -1, and just make sure the top numbers add up on the left and right, and the bottom numbers add up to the same thing on left and right, you will be fine. So just remember that beta particles have the two numbers 0 and -1, and that will be your key to getting these problems correct every time. Let's look at the gamma decay. A gamma particle or a gamma ray is merely a high energy photon of light. We can abbreviate it as H nu, or just call it gamma. I would prefer you call it gamma for now. And just remember that it's not going to affect the mass number, so that's 0, and it's not going to affect the atomic number, that's 0. And it also has a charge 0. You don't need to write the charge, but it's just there to remind you. So you're not going to change the mass number. You're not going to change the atomic number. And you might be wondering, well, what am I changing? What does this even do? Well, it turns out that some atomic nuclei with the same number of protons and neutrons, in other words, the exact same isotope, actually has multiple forms. The protons and neutrons are in a ball that can be shaped in different ways, and the protons and neutrons are arranged in different patterns in that nucleus, and some patterns are more stable than others. And we label the unstable ones with the letter M for meta. Sometimes you'll see M1 and M2 if there are multiple meta forms, multiple isomers of this isotope. Sometimes you'll just see a star. So I've given you an example of each. We have xenon 131M, which is the high energy form of xenon 131, and we have cesium, CS 127 star. And when these undergo a gamma decay, they merely relax to a more stable form of the exact same nucleus with the same number of protons, the same number of neutrons. And it releases energy, and sometimes you will see the amount of energy actually written there. In this case, the first case with xenon 131M, when it becomes xenon 131, it releases a gamma particle with an energy of 634 kilo electron volts. And this is a unit of energy we have not talked about, you are not responsible for. It's just written there to remind you that the energy has a certain value. And we actually know that different gamma particles have different values. And in fact, you can determine what radioisotope was actually decaying by the energy signature that is resulting from it. But you are not responsible for it at all. If you see the number, don't worry about the number. It's just telling you there's a lot of energy there. That's all you need to know. We have kilo electron volts. We have bigger units of mega electron volts, which is 1,000,000 electron volts. We even have giga electron volts for 1,000,000,000 electron volts in other cases. So an example would be technetium or technetium 99M. This undergoes a gamma emission. So technetium 99M will release a gamma particle. So you just have to make sure the numbers are the same on both sides. Well, you're starting with 99 and 43. You're going to end with 99 and 43. The number of neutrons didn't change either. It's 57 in both cases. So you don't change the mass number. You don't change the atomic number. You write down the exact same thing without the M, without the star, and that gives you the new isotope, the new nuclide. And in this case, it's technetium 99. So nuclear reactions, nuclear equations can be very simple, like this simple beta decay where we have carbon-14 undergoing a beta decay to produce nitrogen-14. Very simple, single-step reaction. But some reactions go on until they reach some stable isotope. So if you start with uranium-238, this is the common form of uranium, it undergoes an alpha and beta, and it can do this in multiple different orders as well. But I've shown you one order where you're losing a total of 1, 2, 3, 4, 5, 6, 7, 8 alphas and 2, 3, 4, 5, 6 different betas. And if you were to be given a problem with uranium-238 and they said remove 8 alphas, well, you take away 8 times 4 from the top and 8 times 2 from the bottom, and that gives you what you would get if you had all those alpha decays. And then you do the beta decays. You have, in this case, 6 beta decays. Well, you know each one of those will have no effect on the mass number, so that stays the same, whatever you got. And in this case, you would get 206 because you've lost 32 mass particles. But you've also, since it's 6 beta decays, that means you've turned 6 neutrons into protons, so it would bump the number up. And so we lose atomic numbers from all the alpha particles, but we gain atomic numbers from the beta particles, and we end up with 206 for the mass and 82 for the atomic number. We look up 82, and 82 is lead. And this is the first stable isotope formed in this entire pathway. And there are other ways to write a pathway. Here's one where we start up at the top left. You have thorium-232. Thorium has an atomic number of 90, and it undergoes an alpha, then a beta, and a series of alphas and betas, and in the end, it actually goes through different versions to get to the same final lead-208, another stable isotope of lead, down here on the bottom right. And you'll notice you can go in different pathways. If you started with bismuth 212 here, you can go beta and then alpha, or you can go down alpha and then beta. Sometimes it doesn't matter with some of these isotopes. But you'll notice it doesn't matter. You end up with exactly the same numbers. So if you're told this undergoes an alpha and a beta, it doesn't matter which way you calculate. If you're told it undergoes 3 alphas and a beta, it doesn't matter which ones you count first. You will always end up with the same numbers in the end and the same isotope of the same element. So let's look at some example questions. Alpha decay of curium-246. Well, first you have to figure out what curium-246 is. You look on the periodic table, you see it's number 96. So you have 246 and 96. You're going to be losing an alpha. And it's important that you remember an alpha is 4 and 2 for your mass number and atomic number. So your other product will be missing 4 and missing 2 from the top and bottom respectively. And that gives you 242 and 94. You look up on the periodic table, what is 94? That's plutonium. So your answer is plutonium-242. The beta decay of xenon-118, and that's how you would refer to this, xenon-118. You have to look up what the atomic number of xenon is, 54. This particular isotope's 118. It's a beta particle, so you're going to be releasing a beta particle. You need to remember a beta has the numbers 0 and -1. That means whatever the other product is, there's no change in the mass number, but since you end up with a -1, that means your atomic number of your other product, of your X, must be bigger by 1. So 54 minus that -1, or just simply 54 plus 1, is 55. And now you look up what 55 is. That's cesium. So our product is cesium-118. And if you look at the beginning, we start with xenon-118. We end up with cesium-118. If it undergoes a beta, you don't touch the top number, and you just bump the proton number, the atomic number, up by 1, if you're going from starting material to product. Third example, gamma decay of nickel-61 star. So the star tells you, oh, this is a high energy form. Well, this is very simple. You know you're going to be producing a gamma particle which has 0 and 0 for its 2 numbers. You're not going to change anything. So you start with nickel-60 star. You're going to end with just nickel-60. It's as simple as that. So gammas are very easy to deal with. Alpha decay of gold-173. Gold is Au. It has a mass number of 173 or an isotope number of 173. Look up gold on your periodic table. It's 79. You know you're going to lose 4 from the top. You're going to lose 2 from the bottom. That gives you 169 and 77. What is element 77? It's iridium. So your answer is iridium-169 plus your alpha particle. Beta decay of nitrogen-15. Fill in your beta. Remember that your beta is 0 and -1. And now you just have to make sure the 15 on the left is equal to the total of 15 on the right. Well, you ask your question, the beta is 0, so you ask the question, what plus 0 is 15? Well, it's simply 15. That's easy. And 7 as your atomic number is equal to what plus -1? Well, what plus -1 is 8 plus -1 is equal to 7. So we know that our new atomic number is 8. Our mass number didn't change. We look up what 8 is. That's oxygen. So our answer is oxygen-15 with a beta particle. And the gamma of protactinium-234M, M tells you it's an unstable form. simply remove the M, and you have protactinium-234 as your product. Okay, so let's look at some other typical problems you might get on an exam. And you'll notice in here, the blanks may be the product nuclide, the radionuclide, or it might be the starting radionuclide. So as long as you remember that alpha is 4 on the top, 2 on the bottom, beta is 0 on the top, minus 1 on the bottom, and gamma is 0 and 0, these will be very straightforward. You're always going to look at the top numbers and make sure they add up left and right are the same, and the bottom numbers add up left and right are the same. And if you do that, everything will be straightforward. So let's look at this first example here. We have an alpha particle. The second you see an alpha particle, think 4 and 2. Oops, 4 and 2. You see a beta particle, think 0 and minus 1. See a gamma, think 0 and 0. And if you do that, these will be quite easy to do. So you're going to be looking at only the top numbers first, and then only the bottom numbers. And when you do that, you realize you have a top number here. What plus 4 equals 209? Well, it's 205, obviously. And what down here, what plus 2 equals 83? Well, that's 81. So we know our numbers are 205 and 81. We then go to the periodic table and look up 81, and that is thallium. Now, it's very important to mention here, whenever you're going to the periodic table, the only thing you can get from the periodic table when you're doing nuclear equations is the atomic number. You will never get mass numbers or isotope numbers from the periodic table. Why? Because each element has many different isotopes, and they will all have their own mass number. So the only thing you can find on a periodic table is the atomic number. Do not look for mass numbers or isotope numbers on the periodic table. They just won't be there. They are just listing the atomic numbers. This is what makes an element, that particular element. 83 is always bismuth. 81 is always thallium. Let's look at the second example. Fluorine. Fluorine 20 is undergoing a beta decay. Remember, beta is 0 and minus 1. Don't mix up the numbers. 0 on the top because it has no mass. Minus 1 on the bottom because you're converting a neutron into a proton. That means the new number has to be whatever will add to minus 1 to become 9. Well, that's 10 minus 1 is 9. 20 is unchanged. So it's 20 and 10 are our two new numbers. So now we're going to look up what 10 is. 10 is neon. So our answer is neon 20. And we would say neon 20 is a product. We don't say the 10 because 10 is assumed by saying the word neon. Neon and atomic number 10 mean exactly the same thing, just like thallium and atomic number 81 mean exactly the same thing. Let's look at the third example. You have silver, Ag, 114 star, undergoes a gamma decay. Well, gamma decays are very easy. You just get rid of the star or the M or the M1 or the M2 and just relax it to the more stable version of the exact same isotope. So it's still silver 114. It's just a more stable form of it. So we just write silver Ag with 114 on the top, 47 on the bottom. Nothing's changed. The next one is a beta decay, but you'll notice it's the starting material we don't know. Well, as long as you remember the numbers 0 and minus 1, this becomes straightforward. 237 plus 0 is 238. I'm sorry, 237, that doesn't change. And 93 minus 1 is 92. We look up 92, and we find that 92 is uranium. Atomic number 92 is always uranium. This particular uranium is uranium-237. So the mass didn't change when uranium-237 underwent a beta decay. And you can write it as beta, or you can write it as an electron. As long as you remember the 0 and minus 1, you'll be good. The next example, iodine 130M. So the M is your tip-off. Oh, it's a high-energy form. It's going to undergo a gamma decay. And that's pretty obvious, but let's look at the numbers. We're going from 130 to 130. We're going from 53 to 53. That means we know the top number is 0, the bottom number is 0. And the only thing you know that has that property is pure energy. And in this case, pure energy means a gamma particle. So we would write gamma as our answer. Next example, we have something undergoing an alpha decay to become tin, Sn is tin, tin 102. Tin has an atomic number of 50. This particular isotope of tin is 102. Remembering that alpha is 4 for its mass number, 2 for its atomic number. We add these together, we add these together, we get our product, which is 106 on the top, and 106 on the top, and 52 on the bottom. We look up 52. We never look up the top number, we only look up the bottom number. So 52 corresponds to tellurium on the periodic table, and that is our answer. Next example, copper 69. Copper is Cu. It undergoes a beta decay. Remembering beta is 0 and minus 1. And whenever you undergo a beta decay, your number will go up by 1. Your atomic number will go up by 1, which makes sense. 30 minus 1 is 29. And since the mass number is 0, you're going to end up with the same mass number, 69. You now look up 30. Always look up the bottom number. 30 corresponds to zinc on the periodic table. So we know our answer is zinc 69. And you'll notice I've written the beta particle with its numbers on the right here. I've just written it in a different form just to remind you that the beta particle is really just an electron that is released from the decay of a neutron becoming a proton. Next example, we have boron 20. Now, right away, if you've been looking at nuclei for a long time, you'd realize 20 is a really large number compared to that 5. Usually you don't find anything much bigger than a couple times your atomic number. 20 tells me right away this has way too many neutrons. And in fact, we see our product is a neutron. So what do we do with that? Well, we have to remember, what is a neutron? Well, a neutron has an atomic number of 0 because it doesn't have any protons. And a neutron has a mass number of 1 because mass number is the total of protons, which is 0, and the total of neutrons, which is 1, so 0 plus 1 is 1. So we can treat the neutron as having the numbers 1 and 0. And I'll give you the numbers on a test, but I'm showing you this just to remind you what a neutron is. It has a mass number of 1. It has no protons, so its atomic number is 0. And now you look at the math here. 20 equals what plus 1? Well, it's 19 on the top. These have to add up. And the bottom, 5 equals what plus 0? Well, that's 5. So we know that the 5 is the same as the old 5, so it must be boron in the end. And in fact, we look at our product. Oops. It is another form of boron. It's boron 19, and we have our neutron product as well. I'm not going to give you problems with neutrons as a single neutron decay, but you will see neutrons being produced in fission and fusion reactions, which will be in a later module of this unit. The last example is carbon 13. Carbon has an atomic number of 6. This particular carbon has a mass number of 13, and you see that it is adding to something to become nitrogen 14. You'll notice the top number has been increased by 1, and the bottom number has been increased by 1. So we know that 13 plus 1 is 14. We know that 6 plus 1 is 7. So we know our answer must have the numbers 1 and 1 as our product. Well, the only thing with 1 and 1 is a proton. You can actually write hydrogen by itself, 1 and 1. This would be hydrogen 1, because the nucleus of a hydrogen 1 is a proton. These two are exactly the same thing. And when and if you remember from acid bases, remember a hydrogen ion, H+, really is a proton. So writing either one of these would be perfectly acceptable. We typically write it as a proton, but there's no reason. We typically write it as a proton if we're bombarding something with it. In this case, we're bombarding carbon 13 with a proton or protons to produce something else. but you will occasionally see it as H1, hydrogen 1, which is a mass number of 1, and all hydrogen has an atomic number of 1. And these are typical examples. You're just filling in the blanks as long as you remember your numbers for alpha, beta, and gamma particles, 4 and 2, 0 and -1, 0 and 0. Everything will work out. If you want to add to your knowledge, protons are 1 and 1, and neutrons are 1 and 0. And with this, we'll stop here.